guys. Welcome. Today we have a speaker for the math curriculum. Also, hey, come on in. And we're so fortunate to have Doug Hamilton here today. Doug is a UIS alum. He graduated. He was a math major, and he graduated like 11 years ago. And afterwards, he went to MIT and for a master. He also served in the Air Force, but that was before he went to UIS. The sequence here is not quite chronological. But anyway, now he just got promoted to VP at Nasdaq. From associate VP.
Yeah.
Congratulations, Doug.
Thank you.
I would like to think that this has something to do with it, but probably not. And he is also the head of AI at Nasdaq. And so today he is going to speak on entropy, neutral informations, and predictions. So this will be recorded. So I ask you to be sure to turn off your cell phone. Okay. Yep, it's your time.
Yeah, I'm going to turn off my cell phone too.
Okay.
Power off. And that'll let what I'm sure are a few more people filter in. Off. Work calls at the moment either. That can be off. Great. Perfect. Oh, look at that. We got all the stragglers are coming in. All right. Well, good morning, everyone. Such a... All right. Perfect. Great. Oh, good morning, everybody, and thank you for having me. I'd like to really thank the math department for setting this up and inviting me out here to talk to all of you today. Last night, I was lucky enough to give an ECCE talk about AI ethics, which is a little touchier feelier than what we're going to talk about today, because today we get to talk about the good stuff, which is one of my favorite topics on the planet, information theory, and really an introduction to it. Our goal today is going to be to talk about some of the basic concepts of information theory, certainly to develop a mathematical understanding of what it is we're doing here, as well as some of the kind of the computer science or early computer science background that led to the development of this theory, as well as its applications in the modern predictive landscape. We're going to talk about how we can use this technology to think about prediction, how we can think about strategy, how we can think about pruning information that we don't need, which at some point in your life, you'll really want to have less information in front of you rather than more. And really just try to develop a very good, what I call a gut understanding of what we can do with information theory. So let's begin. So at the beginning of the 20th century, there was a revolution in communication technology. And with this revolution, particularly around telegraphs, radio, etc., we all of a sudden started asking some really interesting and unique questions that had never really been asked before. Like, how do you turn dots and dashes into words in an efficient way? How do you turn electronic signals into sound? And frankly, how do you handle those signals? Hey, people will moan here. How do you handle those signals even when noise gets injected? Because of course, it's easy to think about it's easy to think about an embedding that could turn dots and dashes into letters. You could have one short dot for A, two short dots for B, three short dots for Z, but it would make spelling words like Ziziva, Z-Y-Z-Z-Y-V-A, take a very, very long time. And then the question is, well, when the rubber meets the road, when we actually go to transmit that signal over a noisy telegraph wire that's hundreds of miles long and has birds sitting on it, how do we then reconstruct the message? Because it's not going to look like it did at the point of origination. And all of these questions really get to, at the end of the day, is asking, what on earth is information? Because we're trying to transmit information in these new novel ways, and we have to both deconstruct it and reconstruct it. And while these are really interesting questions, the answers to what is information have many, many different analogs. And they force us to answer things like, what information do I absolutely need? What information can I ignore, and when can I ignore it? How complex is the information I have, or how complex is my portfolio strategy? And do I have data to actually justify it? And now that I have the data, what should I actually do with it? So all of these questions are things that I think before the dawn of information theory, before kind of the dawn of modern computational statistics, we would leave in the hands of the folks in philosophy departments and sociology departments. And thank God we don't do that anymore. Because for several thousand years, they pondered these things and didn't get very far. And then finally we took over and basically solved linguistics in 50 years. So that's going to be our motivation. Before we jump into it, please. Before we jump into it, I'm also going to challenge us to think a little more like statisticians today than physicists. So the way that I think many physicists, and I think or people who are working kind of differential equation-based simulation think about things is very deterministically, right? You have an event and you have an outcome, and there's a process that relates events to outcomes. A huge amount of research then goes on trying to understand in a great detail what that process actually is. And that's really important for a great many things. However, today we're going to think a little more like statisticians, where we'll have events, processes, and outcomes. But one event, that is one set of observations, can go through a process, and that can lead to a distribution of outcomes rather than a single outcome. In the case of physicists and engineers, very oftentimes, when we focus on the process, we tend to test the process by taking an event and then perturbing it a little bit and seeing how it perturbs the outcome. Here, rather, we'll take the event, push it through a process, and expect that one event can have many outcomes. Ultimately, what this means is that we're going to modify our focus. And rather than being keenly aware of the process itself that leads from event to outcome, we're going to be much more concerned with the event and the set of outcomes that it drives. The process itself remains something of a black box to us. And while that might seem challenging at first or even unsettling, there are a huge number of instances around the world or in our world that we understand in this way. If you would like to, for example, understand why the US economy may collapsed in 2008, we can do this in one of two ways. One way we can do it is we can look at historic collapses around the world, and we can look at the events and the outcomes and try to correlate those events together. Another way we could do it is we could design really good A/B tests. The problem there is that would require us to collapse the US economy on a daily basis for years and years and years just to figure out why it collapsed that one time at all. That's a pretty huge price to pay to run that experiment. So this approach to thing to understanding the world is really powerful when you have to deal with things where the cost of experimentation is unduly high. So let's talk about our model of events. So notionally, our model of events is going to be conditional probability. That is, what's the probability of X given an observation Y? Or a little more notionally, what's the probability of outcome X given an event Y? For example, what's the probability that somebody's phone will ring early in a lecture, given that you've asked everybody to turn off their phones? It is about 100%. But so this is going to be our model of events going forward. Go ahead. So in order to actually dig into what we mean when we're talking about information theory, we'll start by discussing our first powerful tool here, which is entropy. Entropy at the end of the day is about measuring randomness. So what do we mean by that? So to start with, entropy, I think, in my career, has been one of the worst defined concepts in all of physics and math. When I was very, very young, and somebody said, if you were asked what gravity was or taught what gravity was, in elementary school, it's the thing that makes an apple fall to the earth. And a little later, hopefully, at some point you learned it had something to do with, massive bodies interacting with one another. And if you're really a sadist, at some point you find out it has to do with, accelerating bodies interacting with each other across tortuous space-time manifolds. And then if you're really, really a sadist, you spend some time looking into string theory and getting nowhere. But but ultimately what you're doing is it's very additive, right? You're adding additional detail to what you're learning about. So that first definition of an apple, the thing that makes an apple hit the ground, is still true in the case where you're talking about string theory. as is the second definition, as is our third definition. They're additive, they add additional detail. Entropy, less so much. I remember, in I think eighth grade chemistry or physics or something like that, we learned about entropy, and it was simply defined as chaos and disorder. And that's a terrible definition. At some point in time, I think it was actually in a differential equations course, or maybe it was like a mathematical methods of physics course. We learned that it was the thing that destroys initial conditions. And that's a pretty good definition. But you have no intuition as to what it means. And then I think in a thermo course or a stat therm course, you'll learn that it's about degrees of freedom. Also a good definition, but really no intuition as to what it means, right? It's something about the more dimensions you have, the more entropy you have. So let's see if we can come up with a better definition. Oh, here's a better definition. Entropy is the degree of uncertainty or randomness in a system. And what we look at here is the equation for Shannon entropy. And all it's saying is that if you have a discrete number of event outcomes I in your set of outcomes X, then the total entropy of that system is the sum of the probability of the outcomes log to the probability of the outcome. And why is this the case, right? Well, this is the case because the more options we have, the more random the event is. The randomness of entropy is a function of the probability of the events. So, for example, if you have 2 outcomes, we'd expect that to be less random than an instance where you have 10 outcomes. But if you have 10 outcomes and one outcome has a 99.9999% chance of occurring, and the other one has the rest having a very tiny percent, it feels less random. So something about the probability distribution between the events also matters as well. Then lastly, oh man, I did a good job with that one. Lastly, the question is why base 2? So the reason why we use base 2 here is that the entirety of the world can be decomposed into yes, no scenarios, right? For all of my computer scientists in the room, at some point, maybe you studied binomial trees, and you note that if you go deep enough, you can get enough outcomes to completely cover the space, right? Because 2 to the n grows really, really quickly. So we can always decompose the world to an arbitrary level of resolution by decomposing it to more and more binary decisions. And this really is what brings us to Shannon's notion of entropy. So let's do a gut check. Let's pick up statisticians' two favorite toys, a coin and a 6-sided die. So each of these are going to be fair to start with. Our coin is going to have 2 outcomes, heads and tails, 50% likely each. And our die is going to have 6 outcomes, each 16.7% likely each. Anybody want to hazard a guess as to which one of these, before you go through the math, is going to be a higher entropy system? That is, which one is going to be more random? Come on, somebody's got to be brave. Worst case scenario, you're wrong and you're shamed forever on YouTube. Well, all right. I'm going to say that my gut feel on this is that the dice are going to be more random. And we can think about it as, if I just had to guess like what the outcome was going to be for each of these, with the heads and tails, if I guessed randomly, I'd be right about half the time. And with the dice, I'd only be right about 1 out of every 6. There's more outcomes. It's simply more random. It's likely going to be a higher entropy system. So let's do it. Well, if we actually go through the math, what we find is that our coin flip contains 1 bit of entropy. And our die contain 2.6 bits of entropy. So where else do we encounter bits? Come on, somebody's got to say it. No? All right. So we also encounter bits when we think about memory and memory allocation, right? All right, cool. So it's kind of interesting that we've chosen to actually state entropy in bits, or at least it's interesting to me. And certainly, the fact that the coin flip has fewer bits of entropy than the die checks out with our gut that the coin flip is less random. But why does it matter that it's 1 bit? Or let's say we change that then from our fair die to now a die that has a 90% chance of being a 1 and a 2% chance of the other outcomes. How about now? Well, now it's less certain which is more or less random. But we can go through our math and we can find out, well, that our coin flip contains 1 bit of entropy or 1 bit of information. And our dice roll has 0.7 bits of information. We'll give these guys a moment to sit down here.
You're drawing crowns.
Yeah. Oh man, we are standing room only. That's fantastic. Oh, yeah.
You're drawing big crowds.
Yeah. All right. So when we say that a coin flip has 1 bit of information, a dice roll has 2.6 bits of information, and our rig die has 0.7 bits of information, we literally mean that they have 1 bit of information, 2.6 bits of information, and 0.7 bits of information. So what this means more practically is that our coin flip can be encoded into 1 bit, right? Well, and we can think about it. 1 bit, we could make the heads 1 and the tails 0. Cool, 1 bit. Our dice roll, which is 2.58 bits, can be very efficiently coded in 3 bits. In fact, what we'll see later is that our 3-bit encoding actually causes us to overfit the dice. You can't really encode things onto 2.6 bits. And likewise, that our rig dice roll can be over encoded onto 1 bit. How do we actually do that? Well, here we see our 1 bit encoded into heads, tails, 0, 1. Our 2.58, however, is a little harder, right? If we tried to encode it onto 4 bits, we would be underfit to the model. Our encoding would be underfit. That is, we'd really only be able to encode, onto 2 bits, we'd really only be able to encode 2, 3, 4, 5, 1, 2, 3, 4 onto those 2 bits, and we'd completely miss out on 5 and 6. In modeling terms, we call this being underfit. And what that means is that we're not able to actually model the entirety of the event into our model of events. The event itself is 2.58 bits of information. We've only allocated 2 bits for the encoding. Likewise, we can encode this onto 3 bits. Here we can encode 1, 2, 3, 4, 5, and 6, and we're left with a whole bit left over that we'd have to encode to nulls. This is what we would call overfitting. Because fortunately, we know a priori that we don't need to use 0, 0, 0, 0 and the bit 1 and the bit space 1, 1, 1, 1 in this. But in the real world, we're not dealing with dice rolls. We're dealing with situations where we don't know what the actual appropriate encoding ought to be. So what we likely do there is encode something else. And this is what we mean, frankly, when we say a model is overfit, that we have too much information. We have information in the model that is not reflected in the real world. So now let's talk about things we can do to improve the entropy or reduce the randomness of a scenario and talk about conditional entropy. So one thing that we've discovered is that a fair die has more entropy than a coin flip, which has more entropy than our rig die, right? So fair die has more information than our coin, and that has more information than our rig die. So here's the question: how would we figure out, excuse me, if our die are fair or rigged? Sorry, that's not it. So how do we figure out? So if we have a fair die or a rigged die, where would it land in all this, right? Well, if it's fair, it's over here. If it's rigged, it might be over there. So that brings us to conditional entropy, right? Where we're trying to figure out based on our observations. Okay, that's what it was. Sorry. It's been a long day. So suppose we give you die and you don't know whether it's fair or rigged. How much entropy does this situation have? Well, if it's fair, it could be in any of these areas. And if it's fair, it would end up over here. And if it's rigged, it ends up over here, right? So with conditional entropy, this is kind of the evolution of entropy, right? And all we're doing here is we're taking an observation Y and applying it to our probabilities to see what the new entropy is. I usually put that this is not important because last time I gave this talk, I gave it to a less technical audience. But I'm going to rescind that comment and say this is actually very important. It's very important to note that when we add the conditional element here, that our new entropy is not the entropy of the event, but the entropy of the event given the observation. Why is that important? Well, that is hyper important because under no circumstance is the entropy of an event greater than, or sorry, the entropy of an event by itself less than, strictly less than, the entropy of an event given any observation. Again, we can think about this, we can take kind of a gut feel on this. Suppose that you know that today, that in general, in mid-April, in Illinois, it's going to be sunny. You can take a guess at the amount of information you can take a guess about whether or not it'll be sunny tomorrow without any additional information. And there's going to be a certain amount of entropy, right? A certain amount of information in that event, right? Will it be sunny tomorrow? And if I tell you that I am wearing, today I'm wearing brown shoes, you could still take that guess. Would that increase the entropy of the situation? No. Would it decrease the amount of entropy? Probably not, because the color of the shoes I'm wearing don't have a lot to do with the weather in Illinois tomorrow. However, if I told you instead that Wonderground was calling for rain tomorrow, that might change your guess significantly. Because now you've made an observation and you can incorporate that, and that is going to reduce enormously the entropy of the scenario, right? You have new information, this new observation reduces your uncertainty, and therefore it reduces the entropy and makes it easier to understand what's going on in the world. So information is a great way to reduce uncertainty and reduce randomness as a result. And that's kind of what our conditional entropy is telling us. So let's look at an application and let's look at the entropy of portfolios. So when we talk about a portfolio, what we're really talking about is a set of stocks that,
This.
All right, give it a second here. I'll turn it on again. I'll keep talking. So what we usually mean is that we're talking about the entropy. We're talking about a set of stocks that are going to give you a certain exposure to certain risks and certain returns. When you want to change your holdings in a portfolio, it costs money to do so because there are trading costs involved. And when you want to analyze your portfolio, there's certain risks you want to avoid, like something called a concentration risk. And how concentrated your portfolio is really a measure of the entropy of the portfolio itself. So one thing that we might do, I'll give these guys a minute here.
That's interesting. Uh-oh. Oh, the light bulbs I get is just
The light bulb is what?
you just give it up.
Oh no, no. Okay.
But online audience can still see you.
Okay, well,
Do you think you can, verbally describe your slides with these guys?
I think I can. I think this is going to be interesting.
Yeah.
All right. Cool. Let's do this, guys.
Yes. Hey, come on.
All right.
Oh, it's on now.
Oh, it's on now.
Get up. Go magic.
Let's hear it for the projection. Well done, thank you. All right. So all we had to do was we had to threaten that we're going to do some whiteboard work. And the projector knew its job was on the line.
So you give it some information.
Yes.
You
Yeah.
give it some information.
Yeah. All right. So let's talk about portfolio. So the portfolio we're going to look at here is three major stock exchange groups around the world. ICE, the Intercontinental Exchange, who owns the New York Stock Exchange, as well as several others. The London Stock Exchange, based in anybody? There we go. That was good. Based in London. And of course, the best stock exchange, Nasdaq. So the first place we might want to start is what's the maximum entropy that we can achieve with a portfolio like this? Well, we could actually show that this is the maximum entropy, right? And that will, I'm sure, be on your homework tonight. And the maximum entropy here is effectively a uniform distribution of holdings across all the firms. That has 1.58 bits. 1.58 bits. So if we want to have a portfolio that has minimal concentration risks, we want to maximize its entropy. Well, where this starts to become very useful, though, is not just when we're thinking about maximizing the entropy of the portfolio, but when we start thinking about other ways we could hold this portfolio. For example, we could try to match the entropy of the portfolio to the entropy of these companies in market capitalization, right? We could try to make sure that our portfolio is below some tolerance, some entropy tolerance when we're talking about concentration risk. And just give you an idea what I mean by concentration risk. If we had Nasdaq, ICE, and LSE, we might say that our that we want to have less than 1.2 bits of entropy in it. And what that would basically mean is but greater than 0.8 bits, right? And what that would naturally mean is it would put a limit on the types of holdings that we could have, right? We couldn't have, for example, 100% of our portfolio in Nasdaq because that's a 0-bit situation. We couldn't even have 90% or 80%. So it kind of put natural limits on the maximum exposure that we could have. And it's also nice because it's one constraint that we have to put on our optimization problem now, rather than having to say, well, Nasdaq has to be between these bounds and ICE has to be between that bounds and LSE has to be between these bounds. And so it's a much nicer way to decompose the scenario. So now that we've learned a little bit about entropy and measuring randomness and information in the system, we'll talk about mutual information. This is where it starts to get a little meatier, because this is where we're actually going to talk about prediction. And in particular, what we're going to talk about is prediction as imitation. Because really, when we're trying to predict something, we're trying to build whether it's an explicit simulation or an implicit simulation, a simulacra somewhere that helps us understand how two things are related. So we'll start by talking about 3 flavors of prediction. The first is the one that we're probably all familiar with. That is, if I asked you what the price of Nasdaq is going to be tomorrow, you would all say to the moon. And, and that's trying to predict future information. I could also ask you, I've got some number behind my back, right? Between 1 and 5. What do you think it is? I'm putting you on the spot.
3.
3. You're wrong. It was 2. You're very close. And what you're trying to do there is read my mind, right? This is still a type of prediction because you're trying to predict what's behind my back. You're not looking into the future. It's still a type of prediction. I could also ask you, what did I have for breakfast yesterday? Presuming that you don't know. Okay, take a guess. Croissant. That was pretty close to it. A sausage, egg, and cheese sandwich, but pretty close. So that, again, you're trying to recover information from the past. I'm going to claim that that's also a sort of prediction. Because the thing that really ties all of these together is that prediction is the task of recovering hidden information. Who here's ever heard of the phrase a hidden variable? Nobody? Okay, good. Glad Haichi has. All right. So what we mean by this is when we make a prediction, we're trying to learn something about a variable we don't see. The reason why we oftentimes think about prediction as predicting the future is because the future is purely unknown to all of us, right? Nobody knows what's going to happen tomorrow. Not Madame Cleo, not Warren Buffett. So as a result, it's always hidden. But information can be hidden in other ways. If I show a computer an image of a cat and say, is this a cat? Does the computer know that that's an image of a cat? No, it's got to make a prediction about whether or not it's a cat. So we can either in the past be reconstructing information, in the present uncovering information, or looking to the future to predict information. And so long as what we're looking at exists beyond our observation boundary in some sense, then we're making a prediction. So let's play a game. This is going to be a really, really boring game. We're going to flip a coin and record it. Then we're going to flip a second coin. And if it's not the same as the first, we're going to keep flipping the coin until we stop, and then we'll record it again. And I'm going to ask you, what's going to be the final outcome of that game? So we can actually see it kind of here, right? If you flip heads, then you flip again and it's heads, you stop and you have heads, flip heads and you end up with tails. You flip again until your heads, you flip tails, you keep going until your tails. That's the game. So we might want to know we might want to understand something like what does that first flip tell us about the last flip, right? And that's where mutual information starts to kick in, which basically says, what's the probability, and mutual information, this is obviously even bigger equation than we've had in the past, but really what mutual information is telling us is that if X and Y are independent events, then there's 0 bits of information relative to X and Y. And if X and Y are dependent events, then there's some bits of information. So what it tells us is, what does an event X tell us about an event Y? So let's go back to our original game and think about mutual information again, right? Because again, what mutual information is measuring here is the joint probability times log base 2, because you can decompose anything into yeses and nos, over the joint times the marginals, or times the independence. So let's do this again. We're going to flip a coin. We're going to record it. Then we're going to flip a second coin. If it's not the same as the first, we're going to reflip without recording. If it is the same as the first, as soon as it becomes the same as the first coin, I'm going to hide that coin and not tell you what it is. And then I'm going to ask you to guess the second coin. But here's a catch. You can ask for any one piece of information in the world to try to guess that second coin. Of course, the information you should ask for is what was the first coin, because that first coin is always going to be the same as the last coin. So the mutual information, they have perfect mutual information between the two. This has applications to analyzing strategies in the stock market. So 2 very simple strategies that we have in the market are something called momentum and mean reversion. And a momentum strategy says, and this is one market regime that you'll see, that if the stock market went up yesterday, it's going to go up again tomorrow. A mean reversion, and basically the premise is times are good and things are going up, and when things go up, they tend to keep going up, right? Pretty good. Or times are bad, when they go down, they tend to keep going down. So another hypothesis we might have, though, is when things go up, they become overvalued, right? Because people bought willy-nilly. They said, "Oh man, that Musk guy said something about Dogecoin. Clearly it's going to the moon," and then it doesn't. So you buy some, you lose some money, and then you feel very sad afterwards. Excuse me. So this is known as mean reversion. If it went up yesterday, it's more likely to go down tomorrow. These are really, really simple strategies. Did anybody here not understand how to implement a momentum strategy? Right? Pretty easy. If the market went up yesterday, buy this morning, sell this afternoon, chances are you'll make money if we're in a momentum regime. Mean reversion, if the market went up yesterday, short today, replace tomorrow at the end of the day, chances are you'll make money if we're in a reversion strategy. So that's how they work. Really simple. And when we look at what we're seeing here is from 2016 to 2022, the performance of momentum and mean reversion strategies in the market. So these are really simple. And of course, they're correlated. They're always correlated. They provide perfect information of one another, because if you bought today in a mean reversion strategy, you should be selling in a momentum strategy, or shorting in a momentum strategy, and vice versa. But it also has applications when we're thinking about strategies in general. So what we're looking at here is some research I did with my team back in 2017, or it's must have been 2018. He's like 2018 in there. So that'd be weird if it's 2017. Generating AI-based investment strategies based on alternative data. 2017 to 2018 was a unique time in the market when momentum strategies were really performing very, very, very well. So what we're seeing here is these two AI-generated strategies benchmarked against a variety of other strategies. What I'm going to point out here is that this yellow one right here is an explicit momentum strategy. Hopefully you guys can see that. Yeah. And what we're finding is that all of these other observations we made are highly, highly correlated to that momentum strategy. So these other strategies, which were kind of exotic based on things like Twitter sentiment and Federal Reserve notes, and et cetera, were all basically just momentum strategies. And what we were able to do, because we knew that, is when we were designing our AI strategy generator, which would scan across data sets, scan across strategies to try to create, we called it the Ensemblizer 4000, ensemble-based methods for generating trading strategies. We were able to measure the momentumness or the mean reversionness historically of the underlying data being analyzed in order to correct for that. Because what you'll note is, while certainly there's some correlation, the correlation between the top two lines, which are our AI generated strategies, are much less correlated to the market and to momentum strategies than any of the observations they were making. The only one that's less correlated is our completely random strategy. I would not recommend taking that one, because that one we were just buying and selling randomly, which was fun, but not something I would necessarily recommend. So this is an excellent way to look for bias in alternative data and systematic bias in trading strategies. I'd highly recommend, if any wealth advisor calls you up and says they're selling you some strategy that's got 40% return historically, and they only show you a very short, like 3-year period of time, that you ask them what their momentum or mean reversion bias is. If they can't answer that, you should probably hang up on them.
Oh, did I miss the part that you talk about AI generated strategies? You didn't mention any specific of.
No, we definitely did not.
Okay.
Yeah. I will tell you that we do have a patent on this, so it uses reinforcement learning. Uses reinforcement learning to design strategies based on a combination of a genetic algorithm and a grid search over the feature space in each of the data sets. I think it's pretty clever. Kind of cool stuff. It certainly seemed like
very well.
It performed pretty well, yeah. So we have other applications too here. We're going to talk about optimal guessing as well. So let's talk about 2 ways that we can make a guess. And guessing is really important. Guessing is it's a shockingly important part of your life. I know that in university, as scientists, we always want to make hypotheses and test things very rigorously before we do something. But you can't do that in real life, because if you're sitting there testing stuff, and 10 other people are taking a risk, one of those 10 people is going to be right. And while you're still testing, they're going to be plowing ahead. And you'll ultimately, so you have to kind of take a good approach to managing, reducing risk through testing and taking risk by action. So we'll introduce 2 guessing strategies. Guessing strategy 1 is what we'll call pure guessing. This is a strategy that randomly chooses the outcome from all possible outcomes. And strategy 2 is going to be what we call optimal guessing. And this is a strategy that chooses an outcome that is correct as often as possible without careful study of exigent information. If we look at, just checking how we're doing for time. Oh, we got plenty. We got till 11, right? Okay, cool. So if we look at our dice roll again, our dice roll again, our rigged dice roll with outcomes 1 through 6, 90% chance of a 1, 2% chance of anything else. We'll call this X. A pure guessing strategy here would be, let's guess a number between 1 and 6. We're allowed to use some sense in pure guessing. Like we don't have to guess a 7. We don't have to guess 11. We don't have to guess zero. So a pure guessing strategy is guess anything. I'm going to make the claim that our optimal guessing strategy is to guess 1. Why is that? Well, our pure guessing strategy would be right about 16.7% of the time, even though the dice comes up as a 1 90% of the time. Our optimal guess, always guess 1, is the guess that is correct 90% of the time. Also, our optimal guess maximizes the mutual information between the world, the 90% dice roll, and our guess, or rather our model of the world. I'm going to repeat that one more time. Our optimal guess maximizes the mutual information between the world and our model of the world. So using these 2 tools, we're going to talk about some interesting consequences of information, kind of introductory information theory. The first is my favorite, one of my favorite things to say, because so many people get a little shocked by it, and I'm nothing if not the shock rock equivalent of a speaker, is that causality is pretty overrated. So why is causality pretty overrated? Well, because the mutual information between A and B is symmetric to the mutual information between B and A. Same thing with A and C. And A, as with A and the joint of A and B given C and C given AB. So what we mean by this is that while A might be causing B and A might be causing C, B and C are informative of one another. And in fact, the joint of AB is more informative of C than just A by itself. So it's good to know about A, but it's also good to know about B. And while it might be better to know about A and B to get C, you can still get a pretty decent way just to get C. We already talked earlier about the fact that we're not going to crash the economy every single day to learn about why the economy crashed 10 years or 12, 15 years ago. We also tend not to get in spaceships, fly light years away to far off stars, detonate them, and then do it again and again to learn about supernovas, right? Instead, we look at lots and lots of events that have occurred throughout the universe and try to see what the correlative information is based on the outcomes. So causality is nice when you can get it, but oftentimes you can't afford it. And when you can't, it's pretty overrated and shouldn't stop you from doing things as a result. The second thing I'd like to talk about is what I call the information of rare events. One of my pet peeves when I was interviewing data science candidates is you'll ask them, a question, right? You'll talk to them and say, all right, so you have this data set, right? And, how do you deal with, how do you deal with it? And they're like, okay, well, I go do my feature engineering and I push it through my model and get this out. It's like, okay. What about in the real world when the data is dirty and you have missing values? Well, with missing values, you still get pretty reasonable information, reasonable answers. Maybe I'll fill them in with medians and mean values, or, if they're really clever, they'll say, what I'll do is I'll just take my entire data set, I'll multiply it over and over hundreds of times and just put random numbers in there to try to replicate the known distribution. And if I want to control the risk, maybe I'll get a larger distribution. If I want to be more precise, we use a smaller one. And these are all reasonable answers. And then at some point, what you're going to ask them is, all right, so you've got your model, right? You've got your data, and it kind of looks like this, right? So what do you do? What should you do here? They're like, oh, what we do is we just get rid of that data point and we build a model. Well, and that's kind of when I lose my mind, because rare events have disproportionate amounts of information. We can actually see that here. And this is where I have a mistake in my math. I'll let you guys find it and then you can roast me in the comment section. But we can look at something called the marginal entropy of an observation, which is given here. And what we'll find is that rare events have much more information than their unrare counterparts. For example, if A occurs 80% of the time, you're already seeing where the mistakes are. B occurs 14% of the time, and C occurs 1% of the time. That doesn't add up to 1. I made this late at night. Give me some slack. What we'll see is that the actual marginal entropy of C, which occurs much less often than A, is something like 20 times higher than A. Right? So the information contained in C, outcome C, is 20 times the information contained in outcome A. And if 80% of our dots were above the line here, and I said, what do you do about those? You certainly wouldn't say, well, I just eliminate them, right? Because they're 80% of our data, even though they contain not that much interesting information. What this really means for us is that rare events are events that contain huge amounts of information, and we shouldn't just be getting rid of them, or at least we should be treating them with a goodly deal of care when we do. Moreover, rare events are events of considerable consequence, typically in the real world. I'll give you kind of a grim example. When I was working at Boeing in the factory there, one of the things that people were very concerned about was something called a crane fall, which is when they have these giant overhead cranes that move up and down the factory, right? Moving airplane parts. And once in a great while, usually nothing bad happens, right? Worst case, the common sorts of errors you'll have is you're lowering a wing or an engine, it'll swing a little bit, it'll dent something. And that's bad. That can be a multi-million-dollar mistake. And that's a little more common. That'll happen a few times a month. What would be really bad though, is if you're carrying a wing and you just drop it on the plane. That'd be pretty bad. That's a good example of a rare event that if you just ignored it would be an event of considerable consequence, because that could be $100 million problem. Even worse, once in a great while, you would actually, particularly after a Seahawks game, the crane itself would be driven too far off the tracks and fall onto the factory floor, which is quite tragic, but it's certainly a rare event. And we might want to understand why that happened. And eliminating those sorts of events from our world of analysis means that the most consequential events, the things that are most important to solve, are the things that we're ignoring. So rare events carry not just more information, but more consequential outcomes as well. So with that, I'm going to conclude my talk on information theory for entropy, mutual information, and prediction, and how we use it in the world of finance and elsewhere, and open up for questions and comments.
So I guess that's the link for your article.
Those are the links for my articles. That's right. I forgot to find them. You should totally read those. Those are pretty good. Yeah. Any questions, comments? Anybody have any poetry they want to recite?
I have a question about that AI generated. What's can I ask? What's the return on that?
Pretty good. I think it was I actually shared the stats on it yesterday. So asking for the return is not the way you want to think about this, though it did have good returns. You usually want to ask about the risk-adjusted returns.
Okay.
And the risk-adjusted returns ended up being something like, I think we had a Sharpe ratio of 3.61 at a time when the market had a Sharpe ratio of 2.6. So it's about 50% better risk-adjusted returns than the market.
How do you define risk-adjusted return?
Risk-adjusted returns. So there's many different formulations of this, but Sharpe ratio is usually returns over the standard deviation of returns. Yeah. Mean return over the standard deviation of returns. Yeah, that's Sharpe ratio. So it's a pretty quick and dirty way to measure these things. And the reason why we do that is, let's suppose that you have lower returns but lower volatility, right? So you have like a signal that looks like this versus one that looks like that, right? Better versus worse. Well, I can take out a loan to make myself to get those returns, but my loan also increases my volatility. So if my loan can give me those returns, if my leverage can give me those returns at lower volatility, then that's a better strategy. Anyone? Bueller?
Any questions, guys? Oops.
I'm happy to get 10 minutes of my life back.
I have
Yeah.
one question. Can we go back to the slides of the different strategies and
Yeah, I figured people would want to talk about that. Yeah.
right that one? So is it by time? Oh, okay.
Yeah.
So I was just noticing that this green one is a random.
Yeah.
And it's doing better. Is this the same green?
That does look like it's the same green. Yeah.
Or is
Yep, that is.
so somehow it was doing better earlier.
Yep.
And why do you have any explanation for this? Why?
Yeah, so I'll give you the high level explanation why random might be doing better earlier. And the reason is that markets go through regimes. And what by that I mean, they go through regimes where they're more sensitive to different things. The best example of this, and there's a guy I'd highly recommend you read called Cliff Asness. He's the founding member of AQR Capital, and he writes a lot publicly about quantitative finance. He's known as like king of the quants. He basically started the whole quantitative finance revolution in the mid 90s, and his big thing is what's called value-based value investing, not like your values, but finding companies that are undervalued in some facet and investing in them. And that was a really good way to invest for a long time until it wasn't, when all of a sudden everybody started investing in tech firms, which are growth-based companies, right? So then growth strategies took over. So likely what happened here is whatever the base during this time, whatever the kind of base strategy was of these observations, they just didn't perform well during that time. So, and since we know they're all highly correlated to momentum, this was probably a time when momentum wasn't performing very well. So a random strategy would have performed better. These markets tend to go up. So a random strategy is going to ride kind of the secular trends of the market, where these strategies are tied to, you know, more concretely tied to particular regimes within. Yeah.
So I guess your strategies, really, they both depends on some historical,
Yeah.
data, and so that's why, as time progresses, they're doing better?
Not necessarily. So what we're actually looking at here is the out of sample dates.
Oh, okay.
So this is all out of sample. And I think, frankly, the reason why they just look like they're doing better is because the returns compound over time. And because you're looking at lots of different strategies, which, while they're correlated with momentum, are not perfectly correlated, it means you can create a more effective ensemble-based strategy, right? That can, one of my favorite parts of this actually is, this divot right here, where everybody else kind of just went up a little bit, we went up a lot of it. That I like that one. There's also, I think it's right here where everybody else is kind of flat and we're going up. Those are the moments where you get your gains, right? Because it turns out that a lot of investment strategies are about very, very small gains compounded over lengthy periods. Yeah.
So I want to know the AI strategy, the performance of AI strategy on March of 2020. What happened?
I think the preferred strategy there was short everything. So this was a research project. We actually didn't run it for March of 2020, but we did notice actually a huge shift because, of course, in March of 2020, what occurred is we hit something called what we call like punctuated equilibrium, right? Rather than the smooth right? Like, so markets exist on unstable generating distributions, right? They shift around. Oftentimes they'll shift kind of smoothly, right? That is, the first derivative with respect to time is continuous, but occasionally it's not, because occasionally, the world shuts down, and you can do certain things to track continuous change. Tracking shocks like that is hard, really hard.
That would be one of the rare events.
Yeah, that would be absolutely a rare event. Exactly.
So, is that like rare events have more information?
Yes.
So, how much weight is you will give an AI generated prediction for those rare events?
That's a really, really good question. So I think it depends on how well your AI system has worked on those rare events in the past, right? So we could look, for example, suppose you built a model. Suppose you built a model A, right? And your model A is built on the world X, right? So your model A has some high level of mutual information between itself and the world X, right? But there's some subset of X that we'll call, like XR, right? That's just the rare events of X. So then you might ask, all right, well, how does my model, what's the mutual information between my model and just the rare events? And our ratio here may actually tell us something about the degree to which we should believe our model when we think we're encountering a rare event.